Hi everyone, welcome back to our Rust programming series. In today's video, we are going to explore a fascinating and crucial topic, building safe concurrent programs with Rust's ownership model. Concurrency is key to modern software development, and Rust offers unique features to handle it safely and efficiently. Let's dive in. Concurrency allows multiple parts of a program to execute simultaneously, improving performance and responsiveness. However, it also introduces challenges like data races and deadlocks. Rust's ownership model and type system help us write concurrent programs that are both safe and efficient. In Rust, the ownership model ensures that data is only accessible by one part of the code at a time. This prevents data races, where multiple threads access and modify the same data simultaneously, causing unpredictable behavior. Let's start with a simple example using threads to understand how this works. Here's an example of creating a new thread in Rust. Let's write the code together step by step. The use keyword in Rust brings modules, structs, or functions into scope. Here, std, thread is imported from the standard library, allowing us to use Rust's threading capabilities. The main function is the entry point of a Rust program. The thread spawn function creates a new thread. The double colons are used to call a function or access a type in a module. The spawn function takes a closure, a block of code, that runs in the new thread. Here, the closure contains a loop that prints numbers from 1 to 9. While the new thread is running, the main thread also runs a loop that prints numbers from 1 to 4. The join method waits for the spawn thread to finish. Unwrap is used to handle any potential errors. Now, let's run the program and see the output. Here's what you should see in your terminal. The output may vary slightly in order, but you should see interleaved messages from both threads. Sharing data between threads can be tricky. Rust provides the arc, atomic reference counting, and mutex, mutual exclusion, types to share data safely between threads. Let's see how we can use these types to safely share data between threads. Here's an example using arc and mutex. Let's write the code together step by step. We import arc and mutex from the sync module and the thread module from the standard library. Arc stands for atomic reference counting, which allows multiple threads to own the same data. Mutex stands for mutual exclusion, which ensures that only one thread can access the data at a time. We create an arc that contains a mutex which in turn contains an integer. This allows multiple threads to safely share and modify the counter. We create a vector to store the handles of the spawned threads. In the loop, we clone the arc for each thread using arc clone. This allows each thread to own a reference to the shared counter. The move keyword ensures the closure takes ownership of the variables it uses. Inside the closure, we log the mutex to safely access the counter, increment it by 1, and push the thread handle into the vector. After spawning all the threads, we join them to ensure they complete before the main thread exits. Finally, we log the mutex again to access and print the final value of the counter. Now, let's run the program and see the output. Here's what you should see in your terminal. This shows that all threads have incremented the counter to 10, demonstrating safe concurrent access to shared data. Rust's std sync MPSC module provides channels for message passing between threads. Channels offer a safe way to communicate between threads without sharing mutable state. Let's see an example of how to use channels for communication between threads. Here's an example using channels. Let's write the code together step by step. We import the MPSC module from sync, which stands for multiple producer, single consumer. This allows us to create channels for communication between threads. We create a channel with MPSC, channel, which returns a transmitter, TX, and a receiver, RX. The transmitter is used to send messages, and the receiver is used to receive messages. We spawn a new thread using thread, spawn and move the transmitter into the closure. Inside the closure, we create a string val and send it through the transmitter using tx, send, val, unwrap. In the main thread, we receive the message using rx, recv, unwrap. The recv method blocks until a message is available. Finally, we print the received message. Now, let's run the program and see the output. Here's what you should see in your terminal. This shows that the message sent from the spawn thread was successfully received by the main thread. Rust's async, await syntax allows us to write asynchronous code that is both efficient and safe. Today, we're using Tokyo, a powerful and popular asynchronous runtime for Rust. Let's dive deeper into what Tokyo is, why it's popular, and how to set it up in our project. Before we write any code, let's talk about cargo, toml. This file is crucial for managing your Rust project. The cargo, toml file is used by Cargo, Rust's package manager and build system. It contains metadata about your project and manages dependencies. Here's what you'll typically find in cargo, toml. Package, section. Name, the name of your project. Version, the version of your project. Addition, the Rust addition used by your project, which affects language features and syntax. Dependencies, section. Dependencies. This section lists all the external crates, libraries, your project depends on. Tokyo, this specifies the Tokyo crate, an asynchronous runtime for Rust. Version equals 1, specifies the version of Tokyo. Features equals full, enables all the features of Tokyo, including utilities for networking, timers, and more. You can customize this based on your needs. By adding Tokyo to our cargo, toml file, Cargo will download and include this library in our project, making its functionalities available for use. What is Tokyo? Tokyo is an asynchronous runtime for Rust that provides the tools and abstractions needed to write non-blocking, concurrent code. Here's why it's so popular. Asynchronous runtime, Tokyo handles the scheduling and execution of asynchronous tasks. It allows you to write async code without dealing with low-level threading details. Concurrency. With Tokyo, you can handle many tasks simultaneously. It manages tasks efficiently, whether you're running on a single thread or across multiple threads. Ecosystem. Tokyo includes a wide range of libraries and utilities, such as for networking, I/O operations, and timers. This makes it a comprehensive solution for building asynchronous applications. Performance. Tokyo is designed for performance. It uses advanced techniques like work stealing and cooperative scheduling to ensure that tasks run smoothly and efficiently. Community and adoption. Tokyo has a large and active community. Many popular Rust libraries and frameworks are built on top of Tokyo, making it a standard choice for Rust async programming. Now that we've added Tokyo to our project, let's write some asynchronous code. Here's a simple example. Let's break down the key parts of this code. Use Tokyo, time, sleep, duration. We import the sleep function and duration struct from the Tokyo, time module. Tokyo provides these utilities for handling asynchronous timing. Async fn defines an asynchronous function. The async keyword allows the function to use await. Sleep, duration, from _sex, 1, await, pauses the function for 1 second asynchronously. The await keyword is used to wait for the sleep operation to complete. Tokyo, main. This attribute sets up the Tokyo runtime and allows us to write asynchronous code in the main function. Say_hello, await, calls the say_hello function and waits for it to complete. Let's run the program and see the result. Here's what you should see in your terminal. This demonstrates that the say_hello function executed asynchronously, pausing for 1 second before printing the second message. That's it for today's tutorial on building safe concurrent programs with Rust's ownership model. By using threads, arc, mutex, channels, and async, await, you can write efficient and safe concurrent code in Rust. If you found this video helpful, please like, subscribe, and hit the notification bell to stay updated with our latest content. Thanks for watching, and happy coding!